Stationary wave. Let's set up the apparatus as shown in the diagram. The steps: first, connect one end of a string to a vibrator and the other end to a fixed end. Second, switch on the signal generator. The frequency of the signal generator is adjusted. Then, the incident wave and the reflected wave add or superpose together. At certain frequency, maybe F1, F2, or F3, there are stationary waves formed in the string. What is stationary wave? When the frequency of the signal generator is set to a certain value, F0, the string vibrates with the form shown in the diagram at different time t. For a stationary wave, we see that there are loops and which are always at rest. Second, there are anti-loops A. Particles vibrate with the maximum amplitude. The distance between successive loops or anti-loops is called half wavelength. The particles between adjacent loops vibrate in phase, but of different amplitude. Last, stationary wave does not transfer energy from one end to another end. The relation between wave speed v, frequency f, and wavelength lambda in a stationary wave. Let the wave speed in the transverse wave along the string be v. It's given that the wave speed in the transverse wave along the string is given by square root T over mu, where T is the tension of the string and mu is the mass per unit length of the string. If T and mu are fixed, we have constant speed. The frequency of the wave f is the same as the frequency of the signal generator. Also, wavelength lambda is given by wave speed v over f. Let's see three stationary wave patterns on the same string. Let L be the length of the string, N be the loops, and A be the anti-loops. We have, in all cases, the wave speed is root T over mu, which are the same since T and mu do not change. The wavelength in case 1 is equal to 2L. In case 2, lambda is L. In case 3, lambda is 2L over 3. If the frequency of the wave in case 1 is F0, then the frequency of the wave in case 2 will be 2F0, and that in the case 3 will be 3F0. Notice that At higher frequency, the wavelength will decrease. That means we will have more loops or more anti-loops. Let's compare a traveling transverse wave with a stationary transverse wave. First, for a traveling transverse wave, the wave profile moves forward along direction of wave travel. However, for a stationary transverse wave, the wave profile does not move forward. Second, for a traveling transverse wave, all the particles are vibrating. But for stationary transverse wave, the particles at loops are always at rest. Next, all the particles in a traveling transverse wave vibrate with the same amplitude. However, the particles between adjacent loops in a stationary transverse wave vibrate with different amplitude. Next, for a traveling transverse wave, the wavelength is the separation between successive cracks or successive troughs. For a stationary transverse wave, the wavelength is 2 times the distance between adjacent loops or adjacent anti-loops. Also, the speed of both waves obeys the law speed equal to frequency times wavelength. That is, V equal to F lambdas exists in both cases. Question 1. Part A. This is the stationary wave. At this moment, if particle A is moving upward, then the instantaneous motions of particle B will be upwards, and C and D will be moving downward. For part B, the loops are, there are 3 loops here. The separation between adjacent loops will be equal to 0.6 over 2, which is 0.3 meter. Question number 2. For stationary wave in a string, if the first frequency is f0, the second one will be 2f0, the third one is 3f0, etc., 4f0. Therefore, if the frequency of the wave in figure 2 is equal to 40 Hz, we will get the first frequencies is f0 equal to 20 Hz, and for the third one, 3f0 equal to 60 Hz, and for the fourth one, the frequency is 4f0, which is 80 Hz. Question number 3. Part A. Since at time equal to 0 seconds, particles at P is stationary, therefore this wave is stationary. Waves. Part B. The time from t equal to 0 seconds to t equal to 0.0 seconds is exactly equal to the period, since the wave repeats itself. Therefore, the period equal to 0.2 seconds. The frequency is 1 over period, which is 5 Hz, and the wavelength equal to 1.2 meters times 2 over 3, which is 0.8 meters. For particles Q and S, the similarity is that they have the same amplitude A, and the difference between them is that they are vibrating anti-phase. For part D, the displacement time graph for particle P is this one, since it is always at rest. And for particle Q, since it is vibrating with maximum amplitude, therefore the displacement time graph for Q would be the one with maximum amplitude. Question number 4. Since this is a stationary wave, and at that instance, particle X is at rest, therefore, part A, at the same instance, particles Y and Z are also at rest. For part B, in a stationary transverse wave, the wave speed V still equal to F lambda, which is equal to 50 Hz times the wavelength is 90 cm times 2/3. Therefore, the speed equal to 3000 cm per second or 30 meters per second.